Hello everyone and welcome back. In today's video, I would like to talk to you about a very nice application and a very common application of integrals, which is calculating the center of mass of an object. We're going to have 2 days on this. Today, the focus is going to be on concepts. What is the center of mass? How do you find center of mass of a linear object, of a straight object, if you put masses on top of the object in different locations? And then we're going to connect this idea to what happens if we have a function that describes the density of an object at various positions. So first of all, when someone says center of mass, what are they talking about? There are two different ways to understand the center of mass, and the first way to understand it, and my favorite way to understand it, is as a place where the object balances. Editing Sam, please go ahead and play the clip from this video to demonstrate what we mean when we say that it's the position of the object where the object balances.
Let's begin with a parlor trick that you've probably seen before. Take a fork and a spoon, interlock them, slip a match in between the tines of the fork, and balance it on a glass, or in this case a beaker. And you can make the whole combination balance there. The reason that works is because the center of mass of the system of the fork and the spoon is actually right at the lip of the beaker where it's balanced. So the point of support is directly below the center of mass. The reason the center of mass is at that particular point, it's not actually within the fork or the spoon, it's somewhere here below it. Now, by symmetry, since the fork and the spoon are about the same shape, the center of mass is going to be along a line approximately here. But because the spoon extends way out and the fork extends way out, this will displace the center of mass downward. And so the center of mass of an object does not actually have to be physically within the object.
Now that you've gotten a chance to see center of mass as understood as a balancing point, I want to share with you one other way of understanding center of mass that is particularly common in physics, and that is to understand the center of mass of an object as a point where all the mass of the object would go. If you were to treat the object as a single point. You know, in physics, it's pretty common to treat objects as points, to say, oh, there's something over here at point A. There's, the Earth is over here at point A, and the sun is over here at point B, and the moon is over here at point C, that kind of thing. Now, is the Earth shaped like a point? No. Is the moon a point? No. Is the sun a point? No, it is not. These are spheres. These are three-dimensional objects. But it is common in physics to treat those objects as points instead of as full spheres because it just makes the problems easier to deal with. And if you're treating a 3D like sizable object as a point, where should that point be positioned that represents that object? The point where that point should be located is another way of understanding the object's center of mass. Now, the first thing that I want to talk about is if you have an object which is a line-shaped, straight object, essentially one-dimensional, and you stacked a bunch of different objects, different weights, different masses on the object at different locations, how could you find the center of mass in a situation like that one? Now, I've recorded a quick video for you to demonstrate the situation that is being covered in this section. Editing Sam, please roll the demonstration. Roll the clip. Hello everyone, and welcome to my very low budget demonstration of center of mass for a one-dimensional object. So what I have here on this table is a meter stick, and a little stapler is acting as my fulcrum, and then the masses that I'm going to distribute on this meter stick, I'm just using erasers. So hopefully this is low budget enough that you can recreate this demonstration at home if you're interested. Now, you can see that this yardstick, by default, has a balancing point that is directly in the center of the stick. And that's because, of course, the mass on the left side of the stick and the mass on the right side of the stick are exactly the same. So the balancing point is going to be right in the middle. Now, what I'm going to do is I'm going to go into this yardstick and I'm going to start attaching these sort of masses to the stick in different locations. So here I have a mass, let's say 1 unit of mass is 1 eraser. Here I have 2 units of mass, 2 erasers, 1 unit, and then 1 unit. I'm going to go ahead and distribute these masses on the yardstick, and we'll see how attaching masses to the yardstick will change its center of mass, its balancing point. So here I go, I'm going to attach a mass of 2 units, 2 erasers, to the yardstick in a position, looks like around 10 centimeters to the right of the center. Center is at 50, and here is 40 on the right side. Now if I attach 2 units of mass right there at 40, it's going to shift the balancing point toward that mass. So I would have to move the yardstick to the right in order to get it to balance again. And so now it looks like our balancing point is right around here, at a position of maybe 1, 2, 3 position units to the right of what was formerly the center. Now if I go ahead and attach 1 unit of mass over here at some other position, let's say I position it 1, 2, let's say 20 units to the left of the center. Now the mass in that position has shifted the balancing point once again. So I would have to scooch this mass, this yardstick, back into a position a little bit closer to the center, maybe right around here or so. Balancing point is roughly 1 unit now from what used to be the center at 50. So the balancing point would be like +1 if I think of position as units to the right of the center at 50. And as you attach different masses at different locations, maybe I attach a mass of 3 units all the way here to the far right, to the far left end of the yardstick, then such a heavy mass so far away from the center has moved the balance point way out here to the left side. So let's move our yardstick until it balances again. Yeah, so now our balancing point is located here about 10 units to the left of the center. So position looks like -10 units, it looks like. So now that you've had an opportunity to see my very low budget demonstration, let's go ahead and write down the formula that we use to calculate the center of mass if you have a one-dimensional object and there are n, let's call it n, different objects on this line positioned at various locations. We're going to keep track of what object we're talking about by an index. Let's just generically call it I. And the position of object I is going to be called x with a subscript of I. And the mass of object I is going to be called m with a subscript of I. If you have this notation, then the formula for the center of mass of the one-dimensional object is given by the following formula. The center of mass, often denoted by the symbols x with a horizontal bar on top of it, is found by a fraction. In the numerator of the fraction is a sum from your first object to your final object of position times mass. Position times mass, add all of those together for each object. In the denominator of this fraction is just the total combined mass of all the objects. Now, if you have done any kind of work in statistics, then you will recognize this kind of shape of a formula. This is the same formula as the one for a weighted average. So in the numerator, the sum of position times mass. In the denominator, the sum of only the mass. This formula, this weighted average, will give you the center of mass of the object in a situation like this one. Let's test this formula on the situation that we saw at the end of the demo video. In the demo video, we had a mass of 2 erasers located at a position 10 units to the right of the center of the yardstick. We had a mass of 1 eraser located at a position of 10 units to the left of the center of the yardstick. And we had a mass of 3 erasers located at a position of 32 units to the left of the yardstick. So let's calculate the center of mass using this formula for this situation. So just applying the center of mass formula, in the numerator, I would add together, I would sum up the first mass times the first position, the second mass times the second position, and the third mass times the third position. And in the denominator, I would just add together all of the masses. So if you calculate this on a calculator, this works to be about negative 14.3, if I remember correctly. And so this would indicate a center of mass, a balancing point, which is around 14 units to the left of the center of the stick. This formula can be used if you're dealing with an object with a bunch of separate masses stacked on top of the object in various positions. However, potentially you have an object that has a density function that varies continuously. Editing Sam, please go to the demonstration of a continuous varying density.
So now in what you're seeing here is the same meter stick still being balanced upon the same fulcrum in the form of our little stapler that we've stolen off the secretary's desk. But the game has changed a little bit now, because instead of putting these sort of separate masses in the form of these erasers onto the yardstick, what we have here is basically one continuous blob of mass on top of the yardstick in the form of this lump of Play-Doh, which I've kind of shaped here. And so now, because we cannot think of this lump of Play-Doh as discrete masses in various positions, how are we going to find the center of mass in this situation? So the idea that we're going to use is the same one that we saw in the first couple of episodes of this class, which is this idea of sort of chopping this complicated problem into pieces and then making some simplifying assumptions about what's going on each of those small pieces in order to make the problem simple enough for us to actually calculate. This idea of chopping a complicated problem into smaller problems where you can make some simplifying assumption. So for example here, I might go into this line of Play-Doh and I might chop it up into pieces maybe about 1 centimeter long. And I might say, okay, so let's look at this blob of Play-Doh right here that I've just sliced. I'm going to assume that the height of this blob of Play-Doh on this little chunk is constant. And if I assume that this is a constant sort of amount of Play-Doh, sort of height of Play-Doh on this chunk, then I can take the mass of Play-Doh on that chunk and multiply it by the position of Play-Doh at that chunk, and that mass times that position, that mi times xi, will be part of the sum that goes into our center of mass calculation. I'm going to do the same thing over here. I'm going to assume that the height of Play-Doh on this chunk is approximately constant, and so I'm going to find the mass of this little chunk, and I'm going to take the position of this little chunk, and I'm going to put that into my center of mass sum. And similarly, all throughout the length of this Play-Doh, I'm going to chop I'm going to chop, I'm going to split this into little pieces, and I'm going to assume that the height of Play-Doh on each little chunk of Play-Doh is constant. Calculate the mass of the chunk. I'm going to use the position of the chunk, and I'm going to put that into my center of mass calculation. Now you can see that with chunks this far apart, for example, this chunk right here, definitely the height and the amount of Play-Doh on this mass is not constant, but as you make your chunks sort of smaller and smaller, and you decrease the size of your pieces, decrease the space between the chunks, the amount of sort of variation between the left and right side of that chunk sort of goes away. And this becomes more and more accurate of a calculation. This sort of chop, multiply, and add process that we have seen time and time again that becomes more and more accurate as the space between your chunks and the width of your chunks gets smaller and smaller and smaller.
So now you had an opportunity to see what it looks like when a one-dimensional object has a density function that varies continuously, varies smoothly, and it cannot be thought of as just a bunch of different separate masses stacked on top of an object. Unless you decide to chop up that density function, to slice it into chunks and into pieces, and to pretend that each piece, each chunk, is its own separate object located on the meter stick in a separate position. And that's what we're going to do to think about the center of mass in this situation. We're going to take that density, we're going to take that Play-Doh, and we're going to chop it into pieces. We're going to manually slice it into chunks so that we can think about it as separate objects stacked on top of the meter stick, similar to what we have here. So let's work through an exercise that allows us to utilize that idea. We have an object that's 10 centimeters long, and it has a linear density function that varies by position. Let's suppose that the function that gives me the relationship between density and position is called rho of x. And suppose that that density function is given to me by way of data, by way of measurements. So at position 0, we have a pretty high density. On the left end, a density of 4. 1 unit to the right, 2. 2 centimeters in, density is 3. And then it sort of slowly tapers off toward the right end. So hopefully this data matches the situation in the Play-Doh demonstration pretty closely, where we have, a high density function and a lot of mass stacked on top of the object on the left end, a little dip, a little bump right here with a little bit more density, a little bit more Play-Doh per centimeter, and then the amount of Play-Doh per centimeter begins to diminish and get smaller and smaller. So I tried to reflect the Play-Doh demonstration here in this table. So 2 parts to the exercise. Part number 1, let's go ahead and find the total mass of the object if it has a linear density function described by this table. Now we recall that mass in grams is given as the product of density in grams per centimeter times the length of that portion that you're working with in the units of centimeters. And if you want to find the total mass, that all you have to do is add together all these little bits of densities times all these little bits of length. Now, if I were going to write down the same idea using the notation given to me in this exercise, that I would say that the mass, the total mass that we're dealing with, is the sum of the density on a certain chunk times the length of that chunk. My density function is rho. My positions are given by different x's, and the length of the chunk is given by delta x, the space between positions. So here is this same idea in Riemann sum notation. So we can see that as an integral, if we had a lot of data, this would become the integral long S for integral from the lowermost x value to the uppermost x value of the density function times dx. Rho of x is what becomes of rho of xi star, and dx is what becomes of delta x as the amount of data that we have and the space between the data gets smaller and smaller. Now, we don't have a lot of data. We only have the 11 data points given to us in this table. So we're going to have to stick with a Riemann sum calculation, which will just be an estimate for the total mass, but it's the best that we can do in this situation, so we're going to have to go for it. Now, as usual, it's up to us whether we decide to take a left Riemann sum or to take a right Riemann sum. And as I've told you, my sort of preference a lot of the times is for the left one, really for no good reason. I just like the left one. So I'm going to go ahead with a left Riemann sum using these left values at these left x's on each of the chunks. And my delta x in this case would be 1 because that is the width and the distance between data points. So here what I've just written down are all these left values, these left outputs, multiplied by my delta x, which is 1 every single time, and the sum of these outputs and these delta x's gives me the total mass using a left Riemann sum. So let's go ahead and use a calculator to find out what this number would be. So this works out to be 16.6, and this would be grams because once again, this is the estimated total mass of the object, estimated using a left Riemann sum and using the data in this table. So if you decide to use a right Riemann sum, then you're going to get a different value for the total mass. I think a much smaller value, as a matter of fact, but both of those values are simply estimates for the true mass of the object, and both of those estimates are going to have some error involved. So now we have found the total mass of the object. What we have basically found is this denominator in the center of mass formula, where you're taking the total and adding together all the masses that are on top of your object. And what we have done here is pretty much exactly the same, except instead of being told the mass of each portion directly, we had to calculate the mass of each portion and each piece of this object by doing a density calculation, density times length, and then adding those together. So in part B, they say find the center of mass of the object. And to find the center of mass, we're going to need to think about what happens with this formula in our situation. And in our situation, we really still have to figure out what is going on with this numerator, because in part A, we have already figured out what's going on with the denominator. We have already estimated the total mass. Now, the numerator of the x bar formula has us adding together over all of our sort of pieces, objects, or chunks, position times mass. In part A of this exercise, we saw that the mass of each piece or chunk could be found by calculating the density at a random position within that chunk and multiplying it by the length of that chunk. And since xi star already represents a random position in the chunk which is indexed by I, we can use this same expression to replace the position portion, xi star, that is part of the numerator of the center of mass formula. So the numerator of the center of mass formula could be found using this expression right here, And that addition, that sum, is going to be an estimate for the quantity in the numerator of the x bar formula in a setting like this one. Now, if we had a lot of data, if we did have a lot of data, and our delta x, the space between our data points, was very small, then this sum would transform into an integral. This sum would transform into an integral from the left end of the object to the right end of the object. The xi star would just become x. The rho of xi star would just become rho of x. And the delta x in the back would become so small that we would start calling it dx. So if we had a lot of data, this expression here on the right side is what would represent the numerator of the center of mass formula in a situation like this one, where we knew the density function. Unfortunately, here we do not have a lot of data. We have a rather small amount of data as given by this table. So we are only able to estimate the value of this numerator, give a pretty rough estimate using the table that we have. Now, once again, my fondness is for a left sum. So on each chunk, each piece of this sum, my preference is to use the left end of the x's and the left end of the y's. So I'm going to be using, for example, x equals 0 on the first chunk and y equals 5 on the first chunk. My preference is for the left end. However, if you prefer, you can also do the right end. Totally up to you. Now, if I use the left end values, then xi star would be 0, the density would be 5, and the width would be 1 on that first chunk. So x equals 0, density 5, delta x equals 1 on that first chunk, taking these left values out of that first chunk. Likewise, on the second chunk, it would be 1, the left-handed x, and 2, the left-handed y that I would use for my x value and my rho value, and then times delta x, still 1 in this case. And as well on the third chunk, I would be using x equals 2 and rho equals 3, these left values, 2 and 3. And let me fill in the rest of this information. Okay, so I finished writing it up. If I decided to use the left x and the left rho value on each chunk, then the left x times the left rho times the delta x for each of our 10 chunks would be given by this expression right here. And let me go ahead to the calculator and figure out what this would be equal to. Okay, according to the calculator, this sum is approximately 42 units. And for the record, because this density is in the units of grams per centimeter, and this delta x is in the units of centimeters, and this position on the left side is also in the units of centimeters, this 42 would have somewhat wacky units of grams times centimeters. So now this 42 gives us the numerator of the center of mass formula. This numerator representing the sums of positions times masses. The answer to part A, the total mass of the object, which we estimated to be 16.6 grams, that would represent the denominator of the center of mass formula. So if I put it all together, the center of mass formula says that the center of mass would be located at a position of 42 divided by 16 divided by 16.6 works out to be approximately 2.53. Or based on the way that we have defined positions, In this problem, this would be 2.5 cm from the left end of the object. Which makes sense, right? If I look at this table of densities, the density is significantly higher on the left end than it is on the right end. So we have more grams in the left end of this object than we do on the right end of this object. So it makes sense that the balancing point would be skewed further to the left side than it would be to this very light right side. So this answer makes sense in this situation. So this is how we would use a sum. This is how we would use this idea of chop up, multiply together, and then add over each of these little chunks. This is how we would use a sum to calculate the center of mass of a one-dimensional object if we had its density function. Now, along the way, we've talked about what this problem would become if we had a lot of data so that we could do an integral instead of a sum. So let's use these notes that we've made on the side to write down the integral formula for a center of mass. If you have an object with a density function rho of x, which could be doing anything, and the object that you are working with occupies positions between what we can just generically call A and B, then if you want to find the total mass of the object, which I will call M for short, then all you have to do is integrate from A to B density dx. Integrate from your smallest x value to your highest x value, density function rho of x dx. And that's just because of exactly what we said up here in part A. Density times length is how you get mass. Summing up, density times delta x is how you get mass. And if your data is very small, then that delta x becomes a dx, and that sum becomes an integral long S. So this integral of density dx is how you calculate total mass. And how do we calculate the center of mass? How do we calculate what we call x bar? We've made a note about that as well. The numerator of the x bar formula would become the integral of x times rho of x dx. That's because the numerator of the center of mass formula has position times mass. Position is just represented by our x value. Mass is equal to density times dx, dx when the data is very close together. And instead of that sigma, we just have an integral long S to represent that we have a lot of data. So this is what the numerator would become. And then to complete the formula, we would just have to put the total mass in the denominator. And this would be the integral formulas for center of mass of a one-dimensional object if you knew its density function. Okay, so this is the explanation of center of mass and how to understand center of mass as an integral. Tomorrow we will explore using these two formulas to calculate center of mass in different situations.